space or this Cartesian plane, it's using the eigenvalues of the 8 lambda 8, the Gell-Mann matrix. The two
the y, I think
but
what we're calling
yeah.
y. Yeah, h1 and y.
Yeah.
Right.
So how it gives us the correct angle, because we see that it's 60 degrees or 120 degrees using the eigenvalues of h1 and h2, but we draw it.
But you see that's the whole nice thing about this thing. You don't need to really worry about the basis and so on. You see. That's what. Yeah. Because it just gives you the dot products between, say, alpha and beta, right?
Okay.
By this procedure of defining the co-root, then you have in between the co-root you have some dot product. I mean, by the Cartan killing form, you take it to define the dot products between roots, right? And this is completely basis independent statement. So dot products are basis independent.
If we draw in the h1, h2, it will give us the same angle, or not?
Yeah, but I mean, so now we don't even have to think in terms of the h1, h2, etc., right?
Mm-hmm.
So we already have the relations between alphas and beta, alpha dot beta, right?
Yeah.
By using this co-root procedure. Right? But once you have that, then just by looking at the all the dot products and the norms, then you can draw it completely abstractly, nothing to do with the choice of basis. Then. Yeah, that's it.
But if we want to interpret the result as an angle, are those the abstract angles correspond to what we draw? Or?
Yeah. Okay. I mean, okay. This we will see today. I mean, that's I think towards the end today we'll see that. I mean, so far we talked about the complex Lie algebra, right? And you have this. I mean, so Cartan subalgebra is also you can multiply the complex numbers. Everything you can multiply the complex numbers. But then we will now construct. I mean, not now. Towards the end of this today, that we can show that you can choose a real slice of the Cartan subalgebra where the metric is positive definite. You see.
Taking a slice such
Yeah.
that B becomes positive definite.
On the Cartan subalgebra, right? So okay, there's a big Cartan killing form is defined in the entire algebra. But then we also saw that we have already seen in one of the theorems that if you restrict that Cartan killing form to the Cartan subalgebra, it is non-degenerate, which means it's inverse of this, right? But that still doesn't mean that the metric is like a Lorentzian metric. I mean, we cannot say anything about it, right? But we'll see that actually you can choose a real slice there, where such that it becomes completely positive definite. So once it is positive definite, then of course you induce that metric on the roots via the construction of the co-root versus roots, right? So the roots also live in a positive definite space, positive definite metric space, right? So then you can use all the geometric notions that we have. When you take the dot, so that's the point. But we haven't, I mean, that we'll see in the last point. Okay, for SU3, fine. I mean, we have explicitly by construction, we had we computed all alpha 1, alpha I dot alpha j, right? And then we saw that it was always minus 1 or plus 1 depending on the, and then you can kind of, assuming that there is a Euclidean description, positive definite description, you can draw the diagrams here. But anything else, I mean, yeah, I mean, the last theorem that we started looking at the more details. I mean, see, before that we had just the information. I didn't bring the specs, so it's going to be a bit difficult. Right. I mean, so we saw the basic structure was so if I have a root alpha, some alpha belonging to delta, then the x alpha. First of all, so x alpha exists clearly, right? Because I'm saying that alpha belongs to the roots, so there must be some eigenstate with this the eigenvector alpha. Okay. Then we concluded from this that x minus alpha should also exist. Okay, and that was simply because of the fact that if I have a bx alpha and something here, the only way this can be non-zero is if this guy is some x minus alpha. Right? And since if this had not existed, then bx alpha with anything would be identically zero. if x minus alpha did not exist, right? And then that would be a contradiction with the non-singular nature of B, right? B will be invertible then, right? B will not be invertible then. So therefore we know that this exists, right? This exists and that's not 0. Okay, good. Then through a series of, I mean, have we proven that? No, we haven't proven that yet. Okay, we'll prove it. In the next step we'll prove. But then furthermore, we saw that x alpha with x minus alpha, the commutator, of course, this is going to be in the Cartan subalgebra, right? I think I was calling H as a Cartan subalgebra. Okay. But precisely which element, right? And then we proved, I think it was just the theorem 12.41, 12.4, the first one of that. We proved that this is equal to B of x alpha, x minus alpha, times H alpha. You see, this co-root which we had defined earlier, right? So it is not just some arbitrary element of H. I mean, it is this very specific element. Okay. So you remember the co-root was defined by saying that alpha with any H is equal to or proportional to, let me say proportional to B H alpha H for all H belonging to the Cartan set. And because B is invertible, this uniquely defines H alpha, right? I mean, you choose your constant here, whatever the constant is, CG, let's say, choose a constant, and once you've chosen that constant, then H alpha is uniquely determined. Okay? That was a very important point. And so there's a unique element. So we know precisely what this commutator gives. This commutator gives a number times that unique element associated to alpha. And this is a very important part here, because of course we also have the relation that H with x plus or minus alpha is alpha H, x plus minus alpha, plus minus. But this is for every H, but let's restrict ourselves to alpha here, then this will be simply alpha H alpha, right? Okay. So what we are saying is that if you look at this algebra and compare it with the algebra of SU2, which was the SU2 algebra, I remind you, was we had, I think we were, I don't know what notation we were calling, we were, okay, I think, yeah, we had, I think, sigma plus minus and sigma 3. Sigma 3 was basically playing the role of the Cartan H, yeah. And then this was proportional to, to plus minus, sigma plus minus, right? I mean, this proportionality depends on how you normalize them. You could put a half or whatever, no? But roughly speaking, is that these things. And furthermore, sigma plus, sigma minus was again proportional to sigma 3. Right? This was the algebra, SU2, right? Okay, now compare that. I mean, think of this as sigma plus and sigma minus. Then we are saying sigma plus, sigma minus is proportional to, and this one sigma 3. This is proportional to sigma 3. And furthermore, these are eigenstates of sigma 3. Sigma 3, sigma plus minus is equal to plus minus, sigma plus minus. So we are seeing therefore that for every root, there is an SU2 subalgebra. Right? This is an SU2 subalgebra. It's a subalgebra because it closes. No? It doesn't give you the other elements of the fully algebra. This is a subalgebra. So this is a very important point. So from this we conclude that for every alpha belonging to delta, there is an SU2 subalgebra.
Alpha and H.
Alpha, for every alpha belonging to delta, these guys, which are generated by x alpha, x minus alpha, and H alpha. Yeah, this is the important point. Okay. Once we have this, once we realize this, then we can start getting very, very powerful results. No? Because we can use I mean, we know all the representations of SU2, right? So then you know that everything else in the Lie algebra outside the SU2 should fall into some representations of this SU2, right? This is what one is doing now. Okay, so the first statement that we, after that, the number 2 point, which we, the number 2, okay, there's a little bit of a catch here. We have to prove also one more thing. You see, this was the root space. X alpha belonged to what we call G alpha, right? G alpha is the set of all eigenvectors which have the same root, same alpha root. Huh? But we don't know at this stage that there is only one independent guy, whether this G alpha is one-dimensional or two-dimensional or three-dimensional, we don't know, right? So that is also important to prove now. So that's the next, the steps. So in the second point, we went through the proof that first of all, we need to show that H alpha is not equal to 0. I had this comparison with the SU2, right? In SU2, I was kind of thinking of this as sigma 3, right? But we know for sigma 3, the metric is not 0, right? Sigma 3 metric is not 0. If you write on the Cartan-Killing form for the SU2, then it's not 0, right? That we know. That's easy to see, right? Because if you look at add sigma 3 and choose the basis, say basis sigma 3 and sigma plus, so sigma plus and sigma minus. Okay? Anyway, three-dimensional. SU2 algebra is three-dimensional. So I can just choose this basis. Okay. Then how will the add sigma 3 look like? Okay, it will be 0 here. Here it will be, say, +1 or +2 or whatever, some number, non-zero number. And here it will be minus the same, right? Because these are the eigenstates. Sigma 3 commutation of sigma 3 with sigma plus was, say, +1. Actually, +2, 2i or something. 2i. Okay, it doesn't matter. Whatever it is non-zero, some number. And this is minus. Okay. Now I take the, so B of sigma 3. What am I going to get? I will get the product, the square of this matrix. 0, 1, minus 1. And then again, the same thing, 0, 1, minus 1, diagonal. And then take the trace. When you take the product, I will get 0, 1, 1. Right? Trace will give me 2. So it's certainly not 0, right? But here we don't have such an explicit realization. We are just doing completely arbitrary Lie algebra. So we don't know yet whether this H alpha, which plays the role of sigma 3 of an SU2, right? Does it have this property that this is not 0? So that was the point of the second exercise, to show that in fact it is not 0. Now, the way that one proves this is basically using again to take some.
Because it's there, like the trick that we did last.
Yeah, it was kind of using this trace property. I should write down these expressions somewhere. So let's write down x alpha, x minus alpha was some number, which was bx alpha, x minus alpha times h alpha, and that equations h alpha x plus minus alpha was equal to plus minus. This was the basic roots, basic things that we have already obtained. And what we considered was to look at some invariant subspaces. Invariant subspaces under the action of these three generators. So we know that this is a subalgebra, right? This we know. So now what we are looking at is take the big full Lie algebra, but from that we look at various subspaces which are invariant under this action. Invariant meaning that if it acts on a given vector of that subspace, it gives you back again another vector of the same subspace. So in that sense, it doesn't take you out of that. And that, so this is the basic trick we used last time, and it was that this subspace we chose. That suppose so the idea was to take some beta belonging to delta, okay, such that such that B of H alpha, H beta is not 0. I mean, this is clear. This is from the definition of the core root. This is nothing else but alpha of H beta. Right? That was the definition. Because this was for any H, that's specialized to H beta. H beta is after all an element of Cartan. So this is that. And the fact that such a beta exists, so that this is not 0, follows from the fact that alpha spans the entire dual space, right? So I should be able to find, or vice versa, I can write this as beta of H alpha. Okay. Beta of H alpha is the same, is equivalent, right? Beta of H alpha. So what we are saying is that there must exist some beta such that beta of H alpha is not equal to 0. Right? Because if such a beta did not exist, then we would run into the contradiction, because we already proven that the set of roots spans the entire dual space, right? So therefore it should exist. So with that, then we looked at the what is it called, alpha chain passing from beta. I don't know if this is the right expression. I mean, you know what I'm just passing from beta. And this is basically the set of all roots which are of the form beta plus n alpha. It's called alpha chain precisely because of this reason. Because if I look at the commutation relation of x alpha with x beta, what am I going to get here? It's going to be something which is in alpha plus beta space, right? This will be something inside there. So x alpha plus beta, and then if you apply on alpha on one of these guys, if you take one of these guys inside here, okay, this is going to give me g of alpha plus 2 beta, and so on, right?
Beta plus 2 alpha.
Alpha plus beta.
Plus 1.
2, sorry, you're right. Beta plus 2 alpha, correct. Beta plus, exactly, thanks. Beta plus 2 alpha, and so on. It keeps increasing, right? Shifting by alpha. Whereas if you put a minus here, so plus minus means plus minus here. Similarly, plus minus would mean, plus minus would mean plus minus here. So it keeps going. So if I draw a picture here, beta is here, and suppose alpha is in this direction from there, and beta is somewhere here, then what I'm looking at the entire chain. So beta plus alpha, beta plus 2 alpha, all the way, and similarly beta minus alpha. Okay, this chain. So I'm considering such a chain. So so we are looking at all of g beta and summed over all n, and belonging to all integers. Now this, of course, this n doesn't go all the way to infinity, because anyway we're talking about finite dimensional Lie algebra. So by this, one means that all possible integers which are allowed, which exist. So now, because of this fact, and of course the fact that each of them are eigenstates of H alpha, right? Therefore, this is invariant under the action of these three generators: X alpha, X minus alpha, and H alpha. When you apply these guys, adjoint actions of this on this space, you get back again an element of this space. So therefore, I can restrict. So this was add. Everything was add here. On this space. Then this is invariant. Therefore, I can just look at these actions restricted to this space. This, let's call it V. So I look at this restricted onto V. So I don't care about how it acts on the other spaces. The remaining part. This V is inside the G, right? The full G. But I don't care about other guys. I just want to look at this V, and I can do that because the V is invariant. Right? So I can do that. And then I look at the trace. I just compute the trace of H alpha in this space.
is this some interesting kind of SU2 representation too at the same time?
Yeah, it will be SU2 representation. Yeah, well, I mean, so this is kind of, yeah, I mean, to really compare it with SU2, you need to prove that. Huh? But at the moment, it's just some algebra, which essentially looks like SU2 algebra.
Not both because of the algebra and both with the new structures that we now have X alpha, X minus alpha, and H alpha.
Yeah.
They can act on the chain. So this whole chain
Should be a
is
representation.
also a representation.
Yes. Yeah, that's the point, exactly. I mean, we are not saying that it should be reducible representation. It could be reducible representation. But whatever it is a representation. SU2. And a finite dimensional representation.
So the group is finite.
Yeah,
The algebra is
algebra is finite. So therefore, so then we just look at the trace, but everything restricted to the V space, in that small space, of H alpha, or add H alpha. So we want to look at that trace. But then I can use the fact, so this of course one can directly calculate, because I know how H alpha acts on each of this space, right? There's an eigenstate, so I can just compute it. It is in this space, it will act like, so beta, it will be beta plus, so beta of H alpha plus N alpha of H alpha, right? Because this is these are eigenstates. And then I have to sum over all N. Okay. And what else? Yeah, that's it. And the trace of identity in each of this space. Trace of identity in the G beta plus N alpha. Trace of identity. Is that clear, the identity? Because I mean, H alpha just gives you on A. So suppose this guy had more than one dimension. Suppose there are several linearly independent vectors. Suppose this was three-dimensional. Okay. But on each of these states, each of these vectors inside, each of the, choose some basis. So if it's three-dimensional, let me call it, I don't know, y1, y2, y3, three independent bases for a fixed n. Right? On each of those y1, y2, y3, the action of the add H alpha is going to be the same number. Right? So this number will come out, but then I have to still trace over the three-dimensional 3x3 matrix. Right? So on each of these states is this times identity. Right? And but when I take the trace over that, what am I going to get? I will get dimension of this space. Right? So for example, if this was a three-dimensional space, I will just get a number 3. Because I have 3 states. Right? For each of them I get 1, and trace is sum over everything. Right? So you get that. So it's the dimension of this. That is one way of doing it here. But on the other hand, so far I have not used any SU2-like algebra, right? But now is the crucial point that we want to use an SU2-like SU2 relations. So this I can write, this guy I can write using this relation as so 1 over dx alpha x minus alpha. Right? Remember that I can always, given an x alpha, I can always find an x minus alpha such that this is not 0. Right? So I'm looking at that pair of x alpha and x minus alpha so that this is not 0. So I can divide by this number, there's no problem with that. It's some number. Okay? Non-zero number. That times the trace V add of x alpha commuted with add of x minus alpha. But that's 0. Right? Trace of a commutator will always be 0. Because the trace has cyclic property, so it doesn't, and so it's going to be 0. So this is a very important thing. It is from this relation that we are concluding that computing the trace of the H alpha in any invariant space must be 0. It just follows from this commutation relation. And the fact that this is not 0. Okay, so that gives you a very important relation. So what does that mean? So that means this whole thing, this huge expression must be 0. Right? But now if you look at this here, I can open it up. So this is just, so this is sum. Now beta of H alpha is nothing else but B H alpha H beta, right? That is that, plus n, and alpha of H alpha is nothing else but B H alpha times dimension of G beta plus n alpha. Dimension, this is dimension, some integer. Could be 0, so for some of them it might be 0, right? But not for all of them is 0. But certainly I know, since I'm saying beta belongs to delta, so at least dimension of G beta is not 0, at least. At least it's 1, because I know that there exists a beta in the set of groups. Now how can this be equal to 0? You see, the dimensions, these D's, are all non-negative numbers, right? And in particular for n equal to 0, it is 1, at least 1, maybe higher than 1, but at least 1. Okay? And for all the others, all the other values of n, it may be 0 or not, but it's going to be some non-negative number. Dimension is always cannot be minus 1, right? Can be 0, plus 1, plus 2, etc. These are non-negative numbers. Okay. On the other hand, I know that for n equal to 0, the first term, certainly this is not 0. Okay. So I get that term here. Okay. So this is certainly not 0. But this is sum over n. This is certainly not 0 because by construction I have chosen a beta and I'm guaranteed such a beta exists, right? Such that this is not 0. So by starting assumption itself, this is not 0. So how can this be 0 if this was 0? If this was 0, then there is no way I could make it vanish, right? So that is why it proves that this cannot be 0. If this is not 0, then okay, then still one has to look at this equation and you will get some conclusions from that. Yeah? But I'm saying that if this was 0, there is no hope of making that 0. Okay? So the first conclusion, therefore, is that this cannot be 0. So conclusion is that the first statement, yeah, this statement, this cannot be 0. Is that clear? Huh? To everyone, is clear? Argument?
Can we also calculate sum there?
Yeah, actually the next step, it will take, let me just, we'll come to that step. Actually we'll find that, this quantity will be some related quantity, has to be always an integer, and that integer has a huge amount of information. Okay? So we will arrive at the step in a couple, 2-3 steps. No, calculate meaning, calculate of course for a given Lie algebra, then you can calculate these numbers, right? But certain things one can prove that certain ratios of these guys will be always an integer. No, those things will arrive at. Okay, now the very important point, that was the other thing that we said, that we don't know whether in the G alpha, dim of G alpha is equal to 1 or is it greater than 1? For sure, at least it's 1 because we say alpha exists, right? So at least it is 1, but it might be also greater than 1, right? We don't know yet. So that's the next step to show that actually it's just 1. Nothing, it cannot be more than 1. Okay, but before I erase this, any question on this?
I want to know if there's a problem with the, if we take the adjoint of H alpha in the matrix form that we, the basis with Cartan's algebra and then the roots. So you get diagonalized matrix with alphas,
eigenvalues.
Roots. So, and when you multiply them, you will get another diagonal matrix with square of each element.
Yeah.
And when you take the trace of them, it should be not 0.
That's
it. So it's work with that to prove that statement.
Yeah, but how do I know that the eigenvalues are not complex? At the moment, we don't know anything.
Yeah, that's it.
Some of them may be pure imaginaries. I mean, not clear. Right?
I see.
Yeah. Because it's totally, we are starting from like you don't know anything. I mean, the only thing we know is that, I mean, if you give me an algebra like SU3, we can analyze it and we know that the roots are not imaginary, right? Either all of them are imaginary depending on whether you use anti-Hermitian basis or Hermitian basis. But if all of them are imaginary, again, it cannot be zero, no? It will be just a negative. But here the whole discussion is about, I mean, like we don't know anything about algebra, right? I mean, it's a step by step. Finally, we'll arrive at the situation where we'll prove that this metric is positive definite. So it will take some time. Okay, so the next thing is to prove that, so the next step was to prove that, this is the same theorem, I mean, that 12.4, this is all in 12.4. So dimension of G alpha is 1. And you can, as a byproduct of this proof that I will discuss now, as a byproduct you also see that dimension of G n alpha, n is some integer, n is some integer, any integer, is equal to 0 except for n equal to plus or minus 1 or 0. So for example, 2 alpha doesn't exist. So if alpha is a root, there cannot be a root which is 2 alpha. Again, abstractly, I mean, how do I know? How do I know that in some, I cannot cook up some Lie algebra which doesn't have this 2 alpha, no? But the statement, what we'll see that again, everything follows from the fact that this B, I mean, all of these steps that have followed from the fact that the Cartan killing form is non-degenerate. Just that would imply again this statement. Okay. So for that, again, to prove this, we do the same thing. We just take a different chain, not this chain, but we consider such a space. So consider the V now, not this V, but a space like this. You take X minus alpha. Okay. So this is by X. This is one-dimensional space, right? I mean, this is the one generator, but we are all talking about vector space. So any number I can multiply to this. And in fact, we are talking about the complexity algebra. So you are allowed to multiply by any complex number. So this is a one-dimensional. This is just to say that it's a one-dimensional, one complex dimensional space here. Then I take H alpha, and again allow complex numbers here. H alpha is one particular, a unique element in the Cartan algebra. Then I multiply by C, that gives you one complex dimensional vector space. Okay. And then consider all the remaining G n alpha. Sorry, let me see. G n alpha. Take n alpha. Okay. But here I'm including everything. So note that here, see so this is part of course G minus alpha, right? But I'm taking just one-dimensional subspace there. That X minus alpha such that this Bx alpha, Bx minus alpha is not 0. Okay? So I'm just taking one dimension there. Even though the full space may be higher dimensional space, no? But I'm just picking up one. No? I mean, you can do anything you want, provided you can construct an invariant vector space. That's the only criteria. So let me see if this is an invariant subspace or not. So I take this, and from Cartan, I take just the H alpha, nothing else. I mean, one-dimensional space defined by H alpha. And then here I take everything. If in an N alpha dimension is more than 1, I include all of them. So sum over all N. N positive, and strictly greater than 0. So n equal to 1 up to whatever, integers. Okay. Now this space is also invariant under these three actions, because if you look at, let's say, first let's take step by step. Add H alpha clearly. I mean, because each of them is an eigenstate. of this. So that leaves all this space invariant. So this is okay. Add x alpha is also okay, because you see when you take the commutator of x alpha with x minus alpha, then I just get h alpha. I don't get anything else in the Cartan, just that. So this is fine. When you apply h alpha on, add x, when you take the commutator of x alpha with h alpha, I'm going to get something here in the, for n equal to 1. I will get x alpha times some number. So it will be inside here. And then this is, of course, if I take any obviously an alpha, if I apply add x alpha here, is whatever it is going to be inside G n plus 1 alpha. Right? So this space certainly is invariant under that action. Right? The non-trivial thing is x. This was, of course, obvious. The non-trivial thing is x minus alpha. And that is okay, because if you look at, again, add x minus alpha, okay, it will start pushing you down, right? This way. So if x minus alpha acts on a particular Gn alpha, you're going to get something in the Gn minus 1 alpha, and so on. Finally, when x minus alpha acts on the n equal to 1, I'm going to get h alpha from that relation. Not anything else of the Cartan, just that. When this guy acts there, you're going to get that. Huh? But if you apply this guy here, you get 0. Because the commutator of x minus alpha with x minus alpha is 0. You see. Right? Because, so add acting on this, add x minus alpha acting on that, gives you 0. So that is what I'm saying, that you choose that x minus alpha which satisfies, which has this thing that bx alpha, x minus alpha not equal to 0, because we need that, we'll need this. And you just choose just that x minus alpha, not anything else. Even if the dimension was higher, you pick that x minus alpha which has this property. So then this is an invariant subspace, and then I can again do the same trick. Compute the trace of add h alpha, but that has to be 0 again for the same reason, because this is I can write it as a commutator, and trace of a commutator is vanishing. So this is again trace in the V, in this space. And now I can explicitly calculate directly. So when it acts on this space, I'm just going to get minus alpha, h alpha, right? So I'm going to get here minus alpha, h alpha, with coefficient 1, because I'm taking only one-dimensional space here. Right? Acting on this guy, it gives you 0, because h alpha commutes with h alpha anyway. It's in the Cartan, so that gives you 0. And here, I'm going to get plus n alpha h alpha, summed over n, times dimension of G n alpha. Okay. So this I can take out alpha h alpha, and notice that this is not 0, because this was nothing else but b h alpha, which we have already shown that this is not 0. So this is not 0. So this is not equal to 0. So a non-zero number multiplying minus 1 plus n dimension of G n alpha, summed over n. N is greater than or equal to 1. So n is greater than 0. Huh? So let me say n equal to 1, 2, whatever is allowed in your Lie algebra.
Is it just alpha or n times alpha?
This one is n times, because I'm looking at the n alpha space, right? This is the n alpha, so the eigenvalue of h alpha will be n alpha, root will be n alpha. That's why it's n times alpha. Okay, so this has to be 0. And we know that this is not 0, so certainly this must be 0. Now, how can it be? You see, the n is all positive numbers, 1, 2, 3, etc. And these guys are again non-negative integers. These are all dimension of a space is non-negative integers. Okay. So, and on the other hand, I know that for n equal to 1, at least the dimension is 1. because I started with the alpha, which was a root. So suddenly for n equal to 1, the dimension is at least 1, right? So that is already cancelled. N equal to 1, and just take the one dimension from that x alpha from there, that is already cancelled. The rest of them are all non-negative numbers, so they better be 0, right? So therefore, from this you arrive at an important conclusion that dim G alpha is 1, okay, and dim G n alpha for n greater than 1 equal to 0, for n greater than 1 equal to 0. Yeah.
For both proofs, how did we know that trace restricted to V is equal to 0?
Because again, that is the reason to prove that all of these three guys, I mean, this space is invariant under the action of x. So that was the proof, yeah. So first one has to check that. If you don't check that, then there's nothing, you cannot conclude anything, right? So in any space, so again, going back to what you were saying, that once I know that this space is invariant under these actions, then this is a representation of this subalgebra, no? And therefore you can restrict the trace there. And inside the subalgebra, everything is okay.
Why should it be 0 restricted to that space? Why should it?
You can now just decompose this thing into smaller, I mean, suppose this is some k-dimensional space, right? I can now look at, when I say restrict, I mean, look at this add h alpha, add of these generators, but take just the k by k part, right? That's what I mean by restrict.
What I'm asking is we use the upper equation to show that trace h alpha is 0 on all the sets.
No, even the previous, in proving this, I restricted to V. That V, which was G beta plus N alpha. You want to prove that, right? I restricted to that.
But at some point, maybe I'm not remembering well, but we showed that trace h alpha should be 0, and therefore restricted to V, trace restricted to V is also.
No, that is not the reason. No, that is not the reason. Reason why we were proved is that this I could write as, of course, this from using that relation is proportional to, I mean that this is non-zero, so I can forget about that. So it's proportional to some number times trace of add x alpha, add x minus alpha, right? But the point is that this commutative, this makes sense within this V space. Of course, this will also be true for all G, right? But you don't get any information from that. So what we are doing, looking at is some smaller spaces, which are still invariant under the action of these three generators, right? So that's how we are getting additional new information, right? Because if you take the full Lie algebra, you don't get much useful information. It's true there also. This statement is true. So I mean, it should make sense, right? Because I mean, suppose. So what did we do? We said this guy minus, so this means this minus that, other way around, x minus alpha, add x alpha. That is what it is, the commutator. But I mean, suppose that when add x minus alpha had acted on V, you get some different state outside V. Then you cannot do this equilibrium, you cannot do that. No? So it was crucial to prove that it is invariant.
Once we have an invariant subspace, we can always claim that the relation is always true.
That's right. That's right.
So then we can claim that trace restricted to that space.
Yeah. Okay. Yeah. So that's a very important point now, right? I mean, we have obtained an amazingly result. That if you are in any semi-simple Lie algebra, if I have a root alpha, then it is only one dimensional. There is only one eigenstate with a given alpha. And moreover, if alpha exists, then 2 alpha doesn't exist. 3 alpha doesn't exist. Only a plus and minus, x alpha and x minus alpha. And of course 0 because kappa is there, of course. 0. So, I already mentioned before, I think. Yeah. G alpha for n equal to 2, 3, etc. This is 0. That is what we proved here. Okay. So that was the thing here. Good. So from now, by now, I mean, with all these results that we have, we can almost immediately write down the most general Lie algebra that we can get. So the general Lie algebra will be just like this type. So we have some roots, set of roots alpha belonging to some delta, and the structure is and the Cartan subalgebra. So we have H with K is 0, where HK belongs to H and K belongs to the Cartan subalgebra. This is the Cartan subalgebra. Then H with the X alpha for alpha belonging to some set of roots is equal to alpha H X alpha. Okay, that we already knew. But now we have learned also a lot about the this commutation relations. We have X alpha with X beta. Okay. Now this commutator we are looking at. So there are several possibilities here. Now I should write it, let's say like this. So let's suppose alpha plus beta belongs to the delta. Then we know that this is going to be some number which I call n alpha beta times x alpha plus beta. Right? This we proved, right? Before the previous theorem.
It's an exercise.
It was an exercise.
Yeah.
We also proved it. Okay. So that was that. So this is the case. And then, if alpha plus beta equal to 0, which means beta equal to x minus alpha, then we already have that. B x alpha x minus alpha times h alpha. And finally, if alpha plus beta is not a root, then it's 0. So this structure. And moreover, we know that for each alpha, the dimension of that root vector space is 1. For each non-zero root. Alpha equal to 0 is special, that's a Cartan. But any non-zero root, it's always dimension, 1 dimension. So that's the basic structure. Now we can actually learn a bit more. And that is now, so then that's the next step. So the statement is that let's suppose alpha and beta, there are two roots which belong to delta. Then the statement is that there exists some integers p and q which is greater than or equal to 0 such that, okay, the alpha string through beta, passing through beta. So I remind you again, through beta, that means we're looking at all the roots of the type beta plus n alpha. So that's what I mean by alpha chain, going through beta. Consists of consecutive roots. Okay. In the range between, so with the n, let's see the same notation, n minus p and q. So n is this, n is that. So we're looking at this chain. Okay, now this G is one dimensional. We already proven this is all one dimensional, right? Apart from the Cartan point. So it's a sum over n. Okay, we're looking at this chain, and the statement is that there exists some integers p and q such that the important point here is the consecutive roots, meaning this chain cannot break. I mean, it cannot be that if I draw a picture again here, beta, So here's a beta plus alpha, beta plus 2 alpha, and so on, and beta plus, let's say, q, beta plus q alpha, and you go down here, beta minus alpha, and all the way to beta minus p alpha. So the statement is that, of course, the fact that there should be upper and lower bound because we are looking at a finite dimensional thing, so there must be some upper and lower bound, right? But the important point is the consecutive. Meaning it cannot be that, for example, few of them exist, are in the set of the roots, then there is a gap, okay? Then again, few of them are in the thing, and then again there is a gap, that kind of thing. Gaps are not allowed. So if this guy exists and this guy exists, okay, then everything in between must exist. Okay. That's the thing. And furthermore, there's a very precise relation. Given these integers p and q, there's a very precise relation which is 2 b h alpha h beta divided by b h alpha equal to p minus q. Yeah.
You should always think those betas and alphas like vectors, right? The addition of them.
Well, I mean, of course. When I say alpha plus beta, this is of course to be evaluated on some h, no?
But there are multiple h's in the algebra. It's not.
There are what?
There are multiple h's.
Yeah, for any h, for h belongs to arbitrary Cartan.
Because we just proved that n times alpha is not a root. It's not existing.
No, n times alpha, no, but beta plus n alpha could be.
Yes.
No?
But if it were only just integers, or if there is only one dimension in Cartan algebra, then that would not also exist. Because we could write it like an n times alpha, right?
Yeah. But of course, this is not for general Lie algebra. Yeah, if it's Cartan subalgebra is one dimensional, then nothing more. But of course, now we are doing completely general. Actually, for one dimension, there's only one, SU2. There's nothing else. The SU2 Lie algebra. For Cartan dimension being 1, there's only one, which is SU2. If it is 2, Cartan dimension is 2, Cartan subspace dimension is 2, there are 2 algebra. Actually, there are more, 3 algebras.
One is SU3?
One is SU3, other is SU2 times SU2. You know, because here we are still talking about semi-simple. But a simple algebra, no, the SU2 times SU2 or SU2 plus SU2, at the level of Lie algebra, it's not a simple algebra. But there is one more. That is something called G2. Okay. It's not a classical Lie algebra. This kind of an algebra, that algebra probably in the classical physics nobody knew about it. Classical physics, orthogonal symmetries appear naturally, right? The rotational symmetries. That was natural. That's why people already knew about it. Symplectic appears naturally in the phase space mechanics, Hamiltonian mechanics. So these two things they knew. SUN was a natural generalization of SON once you go to the complex spaces. So these three were known. But this G2 was something which was it was a construction of this kind of a classification. This predicted that there should be another algebra at dimension 2. Cartan dimension 2. Cartan subalgebra dimension 2. And it comes out, yeah. And this G2 is actually playing quite an important role in string theory compactification, M theory compactification. So somehow there's a space for everything, it seems. Whatever you can. Okay, so this is the point. So the point is nothing is missing. If I have the upper limit, because anyway there has to be upper bound, and similarly there's a lower bound here, right? Then the statement is that everything exists. It cannot be that some of them is missing. And furthermore, there is this relation.
Everything means every possible root space?
All the chain, this entire chain exists.
Every possible.
So this chain, this particular chain, beta plus alpha, beta plus 2 alpha, all the way to beta plus 2 alpha, and beta minus alpha, beta minus 2 alpha, all the way to beta.
Yes, does this chain include all possible root spaces, all possible G?
No. I'm talking about this particular chain, beta plus n alpha. So there can be gamma plus n alpha, another chain, another gamma, right? I'm just talking about this particular chain. So which is obtained by applying the raising and lowering operators of x alpha, x minus alpha, right? This is the same thing. Okay, so how do you prove that? Okay, that was the first statement. Okay, let me just prove step by step. So it's again taking the same. Well, I think we've already used that formula actually. So that formula in the previous, the very first thing that we proved in the previous theorem, we exactly considered that chain, right? And so we can again apply that same chain. So we will conclude that as we know that this V is invariant under the action of alpha minus alpha and x alpha x minus alpha. Then we say that trace of over the restricted over V of add h alpha is 0. And then from that we can conclude now what is this? This space is this is nothing else but beta plus n alpha. So okay, so the first let's do the following. I mean we don't know whether this chain is so let's we don't know whether we don't know whether it's consecutive. We don't know yet. Huh? So let me do the following. I will take a part of the chain which is consecutive. You know, meaning supposing for example, let's say there are gaps here. This guy is missing. Huh? Okay. Then you take a chain from here, from wherever this starts, to the highest point after which there again is a gap. Okay. You take one of these chains. You understand what I'm saying? I mean, it could be that the full chain is broken into bits. But take one of the bits, right? But in that one of the bit, every consecutive one is existing. Okay, that you can do. So what is the idea of this? So I take a bit. Let's say, so this say didn't exist. Huh? This did not exist. Does not exist. But the next one exists. Okay, and similarly, then all of these guys exist. But then at some point, the next one here, this one does not exist. I mean, does not exist, let's say. Does not exist meaning it's not a set of roots. It's not in the set of roots. But so all I'm doing is that from here to there, this is consecutive. Okay? So instead of, so let's suppose I say that there is a chain. So I take another space V, let's call it V1, which is now G of beta plus n alpha. So let's suppose this chain starts from beta plus, let me use the same notation, R and S. So R alpha all the way up to beta plus S alpha. So this is one unbroken chain. So it's one of these bits. So this will be R going from, n going from R up to S. So it's a subchain, yeah.
We can eliminate the possibility that they are all does not exist and only the first and second one, the first and last one.
Okay, so I can just apply that to, so first and the last one, so you say this object, so nothing else exists here. So this itself is a one bit. So in that case, n will be from minus p to minus p. There's only one term, right? And similarly that. So it doesn't mean that R and S must be different. No? If it's only one thing, then it will be R equal to S. Yeah. But the only thing is that I'm saying that this is unbroken chain. This part is unbroken. So now we are looking at the trace over V1. So then what we will find, it will be beta plus R alpha evaluated at H alpha, right? Summed over n going from R to S. N going from R to S. Because that's the eigenvalue. These are all eigenspaces. This is the beta plus n alpha is the eigenvalue, but this is to be evaluated for at H alpha, right? So that's that. And then I sum over that. I'm just using, because anyway I also know the dimension of each of them is 1. Otherwise there would have been a dimension also. But since we already know dimension is 1, so this is that. Okay. I'm taking beta different from alpha. So it's, Okay, so then, so what does it mean? So we can just evaluate that. So this guy, the first one, so there's an n going from R to S, beta acting on H alpha, beta of H alpha, and then plus sum n alpha of H alpha R to S, n equal to R to S. Okay. So this is does not depend on n, so I can take this out. The first term is beta of H alpha times the sum of 1. How many are there? This just depends. It matters. How many terms are there from? So it's what? S minus R plus 1, right? So this is S minus R plus 1. Right? I mean, for example, for R equal to 0, there would be S plus 1 terms here. No? So here, what am I going to get? This will be, so what will it be? So I could write it as, I mean, you know, I think you will be much faster than I can do. Do you know what will be the sum of that? I mean, this I can write it as n going from 1 to S, or 0 to S, minus n going from 0 to R minus 1, right? I can write like that, or 1. Let's put it as 0. So this one we know it is S times S plus 1 by 2, right? And this one is minus R minus 1 times R by 2, correct? I mean the upper range, whatever it was, that times this plus 1, right? Divided by 2. So now if you simplify, what do you get?
I think you may shift the.
Yeah, you could shift. That would be give you the same answer. Yeah, you could write it as n goes to n plus r or something like that. Yeah, that's right. Exactly.
It's like.
Yeah, it should be the same formula.
Yeah.
Right? So what do we get here? 1/2, and then you have s square plus s minus r square plus r, right? Which is the same as I can take out s plus r as a common factor, and then you get 1 from here, and then from here you get plus s minus r. Right? So, so this is, so let me just write it down here. So this guy is s plus r times s minus r plus 1 divided by 2. And that's supposed to be equal to 0. So s minus r plus 1 comes out as a common factor. So I can take this out. Right? And then s minus r plus 1, notice, is not 0. Right? Because this upper r in upper range. So even if s equal to r, s minus r would be 0, but s minus r plus 1 will not be 0. Right? So this is certainly not 0. And then you are left with that. And this whole thing should be equal to 0. That is the conclusion. So this gives us an important formula, which is that b beta of h alpha is nothing else but b h alpha s beta. So just multiply this here, 2. So 2 b h alpha will be beta, h beta, and this guy is simply b h alpha is equal to minus s plus r. That's the formula. But so that was for one bit, one unbroken bit. But now let's suppose there is another unbroken bit. Okay, first of all, before is that clear up to this point? So this is an integer. First of all, already it's quite surprising how you can find this, but it's just coming from again using this invariant spaces and using this algebra. Just the same way like in SU2, I mean, how come all the eigenvalues were integer or half integer? No, all that. So this that somehow is related to that. Okay. Now suppose there is another range, which is from R prime to S prime. Let's suppose there's another unbroken bit. We are saying that maybe perhaps many bits, right? So this was one bit. Then maybe there's another bit which is from r prime to s prime. Right? Then I can do the same calculation and I will find the answer would be, in this case, the answer would be minus s prime plus r prime. Okay. So you have this equality. So these two must be equal because this expression did not depend on s or r and so on, right? This was just knowing h alpha and h beta, you compute that, right? So therefore this must be equal. So this is assuming that suppose there is another unbroken chain. Suppose there is another unbroken bit which characterized by integers r prime and s prime, the same integers, the lower limit r prime and upper limit s prime. Then I would have that. But now if I, so then what can happen? I mean, so you see this equality will tell you that, I mean, if suppose s prime is bigger than s, okay, then the only way I can make this equal is if r prime is smaller than r, right? So you see, so there are some two possibilities. If s prime is greater than s, then because I have this relation s prime plus r prime equal to s plus r, then this can be satisfied only if r prime is less than r, right? But now you see what happened. We had this r and s. That was the first unbroken chain, right? The first unbroken bit. Now I'm saying s prime is greater than s, fine. But then I'm saying r prime is less than r. Okay? That's not possible because this bit, when we set this bit, this was an unbroken bit, so that next one guy and this guy is not there, right? Now we are saying that there is a bigger bit with every consecutive member being present. It's not possible. Okay. So therefore, s prime, so there is only one bit, nothing else. So and that is unbroken. So that's why it's the consecutive roots. Is that clear? Yeah, of course, vice versa also. If s prime was less than s, r prime will be greater than r. So again, that's not possible. R prime is anyway less than s prime. Yeah, I mean, if s is greater than s prime, then we will say r is less than r prime. In that case, this would be that, this would be that, and this would be that. So, see, one interval will be inside the other interval. So that is a contract. So it must be the same interval. There cannot be anything else, right? So this is the thing. And then on the other, so going back to this thing, what we said, but I mean, n equal to 0 must be there, right? Because by the assumption, we said alpha and beta are two roots which exist. Beta exists, right? So n equal to 0 must surely exist, right? I mean, so we are saying that this is the range. This is the range of r and s. But I know in this, and we said that this range is a unique range. I mean, there's no other possibility. There's just one range where every consecutive element is existing. But I know that n equal to 0 exists because beta was a root, right? We started with the beta, which was an allowed root, right? So if n equal to 0 exists, therefore this r must be a negative number because n equal to 0 must be part of that range, right? Is that clear? Because this is just because we said there is only one unique bit, there's nothing more. It's not that this n equal to 0 is somewhere outside this chain. Yeah, I mean, it's not, I think, let's see, think about it, let's see. So this chain, so the statement I'm making is this, so this is a unique chain. This proves that there is a unique chain. And that it is consecutive. And it is, and every consecutive element exists. Every consecutive member exists. So beta plus n alpha is in delta, is belonging to delta, where the range is n is less than and greater than or equal to r and less than or equal to s. Right? It exists. And this is a unique thing. There is nothing outside this range. But I know n equal to 0 is inside the range. N equal to 0 is an allowed root. Right? Because n equal to 0 means this is beta. But our starting point itself was that beta was a root. Right? So n equal to 0 is an allowed root. So therefore it must be inside this range. Right? So 0 is inside this range. That means R is some negative number or could be 0 itself. Yeah? And S is a positive number greater than or equal to 0. That is why, so that's why we have this range, minus P and Q. So I just called, this is what I was calling S, and this is what I'm calling R. No? It's just a statement that R has to be a less than or equal to 0 number. So then substituting that, substituting this R equal to minus P, so this is minus P, and S is Q, so you just get this equation, which is that. Okay. Yeah. Okay. Yeah.
I have a question. For beta equals alpha, this does not work, right?
No, for beta equal to alpha, no, so I'm taking beta not equal to alpha. That's what I'm saying.
That was one of the
Yeah.
assumptions, but
Yeah.
if you think what will happen if you take that, so the below expression will be...
Yeah, if you take beta equal to alpha, it is just 2. Beta equal to alpha, so 2 equal to P minus Q. That's what it is, right? So in fact, in that case, we know the chain is, we have just the alpha, 0 and minus alpha. These are the three guys which exist, right? So Q is 1, Q is 0, because we are writing as beta plus n alpha, right? So beta itself is alpha. So this is actually n plus 1 alpha. Okay. But so what is the value of Q? Q is 0, right? And P is minus 2. Okay. So you see that P is 2, because here I'm already writing P as minus P. Okay. So this tells me that Q is 0 and P is 2. So that's, so in that particular case, yeah. Good, so now what is the next step? Yeah, okay, let's also do that. Although this is probably, I mean, you would I think believe it anyway, even if this was not proven. I mean, we have already proven that if alpha is a root, then n alpha is a root only for n equal to plus or minus 1. I mean, 0 I don't count. 0 is just the kappa. So that's all, right? And cannot be 2 or 3 or 4 or minus 2 or minus 3, etc. That we already know, right? But that is integers. I mean, we have said that only for integers, right? What about, I mean, how do I know that perhaps there is not some complex number times alpha? How do I know that, right? That it doesn't, whether the question is it or is it not? I mean, that's a question. Can it belong to delta? Where C is an arbitrary complex number. Because this statement we have proven only for integer, only for C equal to an integer, that we know that it doesn't exist for, apart from plus or minus 1, right? But how do I know it doesn't exist for pi, C equal to pi, no? Or some, how do you know that? So that is a proof here. So let's suppose beta, so there is a root which is beta equal to C alpha. Okay, suppose it exists. Then you apply this formula is general, right? So look at this formula. So it tells you that 2, now if beta is C alpha, then of course this will become C times H alpha, and this C can, this will cancel, right? So you'll get 2C. So 2C, so we are saying that 2C is an integer. Okay. That's one thing. Second, this was because I looked at, I mean, notice that this equation is not symmetric in alpha and beta. You see, the numerator is symmetric in alpha and beta, but denominator is as alpha alpha. Why that is that asymmetry is there is because we are considering alpha chain through beta. If you had instead considered a beta chain through alpha, you would get, here this will be replaced by beta beta. Right? So now do the same thing, but now consider, so this was the result coming from alpha chain through beta. Through beta. But you can now consider beta chain through alpha. Okay. And then we will get an equation that 2b h alpha h beta divided by b h beta equal to some integer. I mean, this is details I don't need. I don't care about the details. It's some integer. But now if beta is C alpha, so then you see this guy becomes C B alpha alpha, but here it becomes C square because H beta. Huh? So this will become 1 over C, so 2 over C. So this implies that 2 over C is an integer. So we have two relations. 2C is an integer and 2 over C is also an integer. Okay. So the only possibility, the very few possibilities. C can be 0, of course. C can be plus minus half, plus minus 1, and plus minus 2. That's it, right? Because I mean, you see, C cannot be 3 half. I mean, from this relation, C can be 3 half, right? But then here, if you plug that here, it will become 1/3. No, not possible. So both these conditions simultaneously imply that the only possibilities are C equal to, so C, only possibility is C equal to plus minus, 0, plus minus 1, half, plus minus 1, or plus minus 2. These are fine. This we already know about the integer case, right? So the thing to check is about these guys. We want to show that this is not possible. Well, this also we know already. This also. Now, what about that? Well, if this was the case, then we are saying beta equal to alpha plus or minus alpha by 2, right? But then this would imply that alpha is equal to plus minus 2 beta. Just multiply by 2, right? But that's not possible because we said if beta is a root, 2 beta cannot be a root. Right? So this is not possible. So this proves that it is not just the integer. I mean, it cannot be any number times alpha, apart from the plus or minus 1. That's it. So that's a result. Yeah, so the last statement, actually we had not proven that. I mean, now I realize. When we wrote down the general form of the Lie algebra, we said x alpha x beta is equal to n alpha beta x alpha plus beta, right? If alpha plus beta is a root. But we had not shown that actually that is commutator is not 0. But that equation is still true. I mean, if that commutator happens to be 0, n alpha beta is 0, right? But now we want to prove that n alpha beta cannot be 0. Right? You remember the general form of the Lie algebra that we wrote was x alpha, x beta commutator. So alpha beta belong to delta. So this will be, there are several possibilities. It was equal to n alpha beta x alpha plus beta. If alpha plus beta belong to delta, then it was equal to this bx alpha, x minus alpha, h alpha. If beta equal to minus alpha, and it was equal to 0 if alpha plus beta did not belong to the roots. But we had not proven that this guy is necessarily, we didn't know anything about this number, right? At the moment, this is just some numbers. It may be a 0, it may not be 0, whatever. Right? But now what we are going to prove is that this cannot be 0. Okay? That, yeah.
There, how can C be 0? I mean, it's 2 over C equals integer, right?
Yeah, but 0 is an integer, right? In the other case, I mean, of course, I mean, yeah, 0 probably I shouldn't write 0, yeah, because 0 is the kata, you know. So yeah, you're right. That's right. Yeah. Then it's just the kata generators. Yeah, you're right. Yeah. So yeah, so then I want to finish this part at least. So we want to prove that if alpha plus beta is a root, so alpha beta belongs to roots, and if alpha plus beta is also belonging to a root, then x alpha, x beta cannot be 0, is not equal to 0. Which basically is saying that is going to be this n alpha beta is not 0. So let's we take the idea, the way to prove this is by contradiction. By contradiction. So suppose assume that this is 0. Assume that x alpha x beta is 0. Then that means that I can consider this chain V is equal to so n going from minus p to 0. Okay. And actually, in fact, I don't even have to look at that. Yeah, okay, let's look at that. So this, if I look at this guy, G beta plus N alpha, this is invariant under the X plus minus alpha and H alpha. So how does it go? So remember, we said that there was this chain, which was, we had this chain which was going from minus p plus, beta minus p alpha, all the way up to beta plus q alpha. Okay? And we said that there is a, if this exists and that exists, then everything inside exists. Right? It's a consecutive step, consecutive chain, we said. Okay? Consecutive chain. So if this exists, that exists, then everything in between exists. That's what we said, right? But now suppose, okay, the root exists. We are saying that this root exists. But could it be that x alpha, x beta commutator is still 0? That's what we are saying, asking. For some reason, this alpha beta happens to be 0. So if that happens to be 0, if n alpha beta is 0, then I can consider a smaller chain. The smaller chain being minus p to 0. Why this is invariant? Well, if I look at x minus alpha action, it goes backwards. But that's okay, because minus p was the minimum anyway. After that, there were no roots, so that was fine. H alpha leaves us invariant. X alpha would move it up. Okay. However, when n equal to 0, this will be x beta here, right? But we are saying that x alpha, x beta is 0. So add x alpha will just annihilate it. Okay? It will not take you to the next one. Okay? Although we have all these roots from minus p to q alpha, where q, under the assumption that alpha plus beta exists, the q is greater than or equal to 1. Correct? So this is an assumption. So we are considering this situation where alpha plus beta root exists. Okay? So in this chain, I know there is a minus p and there is a q, but q is greater than or equal to 1. Right? Because alpha plus beta exists. So at least q is to be 1. Right? Perhaps more, but at least q equal to 1. However, if this commutator vanishes, then I can consider a smaller space. Just stop at the beta. Just look at this part. And that again becomes invariant because when add x alpha x here, it gives you 0. So it doesn't go to the next one. So the next one would be, let's say, beta plus alpha. The next one will be beta plus 2 alpha. All the way up to beta plus q alpha. Right? This was the chain. But if this accidentally happened, then I can just stop here. It doesn't go there. You see? Add action. Okay. So then I can find a smaller space where this will be true. I mean that this trace will be vanishing. So if I take the trace now, so this, let's call it V1. So this V1 is a subspace of the full V. The full V which we use for the first part of the theorem. And now I look at this smaller space. Then this thing over the smaller space must also be 0. Add h alpha. Okay. But that is exactly like doing the same calculation that we did with q and minus p, but just set q equal to 0. Right? Exactly the same computation that we did here. Oh, I erased it. Okay, that part. And therefore, then we would conclude that 2 bh alpha h beta over bh alpha h alpha is, what is it, p minus q? What was it, q minus p? Or? I always get confused with this. P minus q. Eh? So, but now I just substitute q equal to 0, right? So this is p. Okay. But on the other hand, 2b h alpha h beta divided by b h alpha h beta is p minus q. Right? So this would say that q equal to 0, but that this contradicts the thing. Q cannot be 0 if alpha plus beta belongs to it. So this is by contradiction. We prove that. So it's okay. Good. Now just the last bit. I will skip the 12.4 because we have only 2 lectures left. So the 12.4 section I will skip, which I already mentioned to you before, that for simple algebra, it doesn't matter. I mean, in the Cartan killing form, we use the adjoint representation to compute the trace, right? Trace of adjoint of, say, x with adjoint of y. But I told you that it doesn't matter. You could have taken any representation, any irreducible representation, not the singlet, not the trivial representation, but any non-trivial representation you could compute, and again the answer would be, it will be proportional to the same metric. Well, trivial representation also is proportional, except the proportionality constant is 0, you know. But otherwise, if it's a non-trivial representation, the proportionality constant will not be 0. There will be some number, non-zero number, and then. But so this is basically proof of that statement. So, but I will skip that because it's we don't have time. But I just want to cover this last bit, which is what I started from the beginning today. That you have a positive definite metric. There's a section of the Cartan killings, Cartan space, subspace, where the metric becomes positive definite. So that is the idea here. So we already have H alphas, right? H alphas for, I mean, alphas times the entire the co-roots, I mean, entire dual space, right? Alphas. So H alphas also span the entire Cartan subalgebra. So let's just look at this H alphas and consider now a subspace, let's see, which I call H. We were using H for the Cartan subspace, but here it was understood to be complex, right? But now I will take a subspace of this, which I will denote by R, subscript R, which will be defined as simply the real numbers times H alpha, sum over alpha. So in other words, any element of this subspace can be expressed as linear combination of H alphas with the real coefficients. Okay. And in that space, the claim is in this space, if you take the B and restrict it to this HR, the subspace, okay, then this is positive definite, is real and positive definite. Which of course means that you can use all the geometrical, I mean, Euclidean geometry, that things that we know from Euclidean geometry you can apply. You can geometrically think like that. I mean, now there won't be any null vectors, you know, unlike in the relativity you're seeing, right? Like directions which are null. Right? You know, no such strange things will happen. It's positive definite. Okay. So the proof is something like this. Okay. So now you know that we have already in one of the previous chapters. Remember we had already a general formula for the B, H, K, where H and K are arbitrary elements of the Cartan subalgebra, and that was given as sum alpha H, alpha K, summed over all roots, right? I mean, again, this factor of 2 sometimes appears, sometimes does not appear. Huh? It is simply because the factor of 2, when you see factor of 2, it would mean that one is summing over only positive roots. But if you don't have a factor of 2, it means summing over all roots. Okay? So that was a general formula completely. This simply comes from the fact that you, when you write this add H, you just have eigenvalues, right? I mean, it will be diagonal with this eigenvalues alpha H and alpha K, and then take the trace. Okay. Now, on the other hand, we have also seen from the previous discussions that 2 H alpha, H beta divided by B H alpha is equal to, well, I think was P minus Q, right? In that chain, P and Q. But anyway, whatever it is, let me just call it some integers and alpha beta. I denote this, this is just a symbol that, because this integer depends on alpha and beta. So that is what I put here, alpha, beta. But whatever it is going to be some integer. Okay, this belongs to integer. So, on the other hand, I mean, if I just apply this here, so we see that B H alpha is equal to, just apply this, just take this to be both H alpha. So it will be sum, I mean, this is, maybe I should call beta. This is arbitrary, so beta. So this is beta, and then we have beta of H alpha, beta of H alpha. Okay. That's a sum over all beta, but this is nothing else but B H alpha H beta square, right? Summed over beta. This by definition is B of H alpha H beta and square. And now I apply this formula. So this is going to be B H alpha H alpha square divided by, I think, 4. 4 times n alpha beta square. Sum over beta. Okay. So you found a relation. You see the B H alpha is equal to the square of itself times some integer squares divided by 4. Sum of integer squares. So I can get a formula for B H alpha H alpha. So B H alpha is equal to 4 divided by summed n alpha beta square. Summed over beta. Beta belongs to all roots. So this beta is belonging to all roots. Now this is certainly positive, right? This is actually some positive and rational number actually. Now, so if this is a real number, then BH alpha H beta is also a real number, right? Because anyway, this is integer, so it's real. So multiply. So this tells me that both BH alpha and also this is a positive number. This is a positive real number, and yeah. So the B H alpha H beta is also, in fact, is even some rational number. So that's the point. So I mean, if I now look at any combination, let's say some X alpha H alpha, some combinations like this, and take the, say, B of that, B of this with itself. First of all, just take any arbitrary X alpha, two elements like this, and some Y alpha H alpha by beta H beta. So some take some 2 elements like that. Then you can open it up. This is because these are linear objects. So this is going to be some X alpha Y beta alpha beta belonging to the roots, and the B of H alpha H beta. Okay, this we know is a real number. I mean, rational number, and therefore also real number, right? And if I restrict myself that these coefficients X's and Y's are real, then this whole combination is real. So the inner product of any 2 elements inside this HR is going to be real. And when you take the square of this, square of each of them, this is positive. So that way then you basically prove that it is positive definite space. Okay. All right. I mean, very generally to prove this, is that convincing to you or not? That this is positive definite. This is say, let's say, I mean, I can choose from this some basis, right? I mean, like for SU3, what we did. I mean, there are several roots: alpha 1, alpha 2, alpha 3. You can just choose some basis, alpha 1 and alpha 2. Choose any basis, because this is overcounting. I mean, the actual dimension of the Cartan subalgebra and the number of roots may be much more than that. Number of roots may be much more than that. Like in SU3. You had H1, 2, 3, alpha 1, alpha 2, alpha 3. So we have H1, H2, H3.
But to use this, we are restricted to choose 2 roots from possible roots, nothing else. I mean, HAs are fixed somehow.
H alpha is fixed.
Maybe more than the need, but they are fixed.
That's
we can only use them.
Yeah. I mean, meaning that that we are going to take the subs. I mean, if you can reproduce a full H by allowing this to be complex, right? And because H anyway spans the whole space, right? So you take that, you just allow complex numbers, then you get the full original Cartan subalgebra in the complex reduction. But now we are taking a real subspace.
Yeah, but in taking this, we cannot choose H alpha like I times H alpha.
No,
Because it's not a root.
that's it. Yeah. So, but I mean, yeah, not I times, yeah. It's only, you only allow real numbers. But you can choose some basis.
So the basis we can choose I times H alpha.
No, basis you choose from the H's. I mean, after all, this just means expanding, no? I mean, after all, what it means, I can write any element as some combinations of this, no? So any element will be of the form X alpha, H alpha, summed over alphas, where X alphas are all real. That's what is the generic term, But I mean, this is a bit overkill, no? Because H alphas themselves are not independent, no? Like we saw in SU3 case. So you can just restrict yourself to, I mean, choose some H alpha, let's say I. So where alpha i's are some basis. Define a basis. No, I know it's possible because we have already shown that this spans the entire dual vector space, right? So I can just pick up this number of alphas which is equal to the dimension of the Cartan subalgebra. Okay, I can find it. Like in SU3 case, we chose H1 and H2, no? Or H1 and H3. You can choose any two. So I choose that and then just expand in terms of this xi alpha I. So it is summed over I going from 1 to the dimension of the Cartan subalgebra. And so, I mean, if I was taking this to be complex, then of course this will not be true. I mean, what we said, BH, I mean, if I allow some complex numbers here, let's say C1 and C2, two complex numbers, then this is not going to be real, right, in general. Because it will be C1 times C2 times a real number. But C1 and C2 may be complex. But so the point is that once you have arrived here, that like the basis vectors, so let's look at the I and Ij, alpha j. So we are saying I is not only is real, it's positive definite. This is important, right? It's not negative. It's not negative. It's positive. And alpha I with alpha j are again real numbers. This need not be positive. No. Then this whole space is a positive definite space. Take any element inside here. Its non-square, length square will be positive. That's the statement. Yeah. Okay. So basically what this means is that you can think of the root space and root space is a dual of this space and the Cartan space has, in the usual geometric sense, no? Like what we are familiar with, Euclidean geometry. I think that's what we are most familiar with. The Lorentzian thing is a bit complicated. All right, so I think I just stop here now, and then the next, I will directly go to because of the lack of time. I will go the next two lectures. I will just go directly to the chapter 14. Chapter 14, I will not cover everything. Just some basic ideas about the simple roots and how you can classify. I've already explained to you this definition of positive roots and negative roots in the context of SU3, right? But now we'll just do it for general, and also the notion of simple roots. Okay, that again we'll use introduce it in general, and then yeah, we'll see how much we can go in the two lectures. Any questions? Yeah. Is it too abstract, all of this? It's too abstract, but isn't it, I mean, don't you feel, when I first studied this Lie algebra, it was during my master's time actually, I mean the roots, and I was amazed at the beauty of this whole thing, you know, how much you can get just from one little thing, non-degenerate metric. You know, it's amazing how, so it's very, okay.
I have a misconception in one thing. For the Cartan space, we have it's infinite. It should be infinite always.
Cartan space, sorry?
Cartan space.
But infinite dimensional or what do you mean?
Because
No,
if
finite dimensional.
we consider h, then h squared must exist inside it.
No, there is no notion of h square in the Lie algebra. It's a vector space. You know, vector space you can only add. You can multiply by number. Yeah.
I mean, if h exists, then acting with h twice also exists. Maybe.
Yeah, but it's not an element of the Lie algebra. You see, I mean, h square, like I will take polymetrics, I mean, sigma 3. Sigma 3 square is identity, right? But it is not an element of the SU2 Lie algebra.
So, what's the dimension then?
No, dimensional vector space is just, in the vector space you don't multiply two vectors, no? You just add vectors.
So just h plus h, I can add
Yeah,
h many times.
Yeah, so you can multiply by any number. That's one thing. I mean, if I have one vector, I can say 10 times that vector is that, you know.
Yeah.
Then you can multiply by numbers, not vector with vector, no.
But with the rising and lowering operators, we proved that here that they are should be one-dimensional. But I can act with them more than infinite times. I mean, I can rise and lower how much I need.
Raise and lower, you mean this chain that we are talking about?
Yeah,
chains.
the root elements,
Yes.
x alpha minus alpha. But for me, I think it's the same as the Cartan elements that you can add. So it should be the same dimension for each alpha, each h.
What did you say, the co-roots, the h alphas? For
H.
each a, for each alpha, you have an h alpha. That's what you say.
I say that for each specific h, I can add it many times, and
So 10 times actually, say.
yeah, and I consider it's a new dimension.
Not a dimension of, I mean, let's say, I mean, think about our three-dimensional space, right? It's three-dimensional, but there are infinite number of vectors, right?
Right.
Any point in the three-dimensional space is a vector, right? Because you can always join a line from the origin to that point. The infinite number of elements are there, but dimension is 3.
For
I'm talking about, take our example,
for
three-dimensional
the
space.
Cartan, if I have specific h, then the dimension is 1 for the Cartan space.
Look, SU3 we had Cartan subspace was 2-dimensional, right?
2-dimensional.
SU3, we saw it is generated by H1 and H2.
For us, 2 it's 1 dimension.
SU2 is 1-dimensional. SUN it will be n minus 1-dimensional.
So, yeah,
I mean, yeah.
it's clear.
The notion of dimension is in the sense of the vector space. I mean, what is the sort of so linear? First of all, you start with a notion of linear independence, right? You say two vectors are, two things are linearly independent. If I cannot write, I mean, it is a say x and y, two vectors. This is a vector space. So I'm talking about vector space first, but all these things are vector spaces. So whatever I'm saying is applicable to all the Lie algebras and so on. So if you say that these are linearly independent if a plus bxy equal to 0, where a and b are some numbers. If you solve it, only solution is a equal to b equal to 0. Then you say, if the only solution to this equation, I give you the x and y, you give me some x and y. Okay? Then I look at this equation. Okay? And ask the question, is the only solution of this equation is A equal to B equal to 0? Then you say it's linearly independent. And similarly, you can have many number vectors, x1, x2, up to xk, let's say. And again ask the question, is this set of vectors linearly independent? Then again you do the same thing. You consider ai, xi, summed over I, where ai's are arbitrary numbers, say real numbers. Although if you're doing complex, you will do complex numbers. But let's take real vector spaces, so real numbers. And you look at this equation and ask whether this can be 0 or not. And if the only solutions are all ai equal to 0, then this is again linearly independent. And now what is the dimension? The dimension is basically the maximal, how many, the set, what is the maximal set you can find of linearly independent guys? Okay? That maximal number is k. If k is this is a maximal set, meaning that to this set, I cannot add some other xk plus 1. If I add some other vector here, then this whole thing is not linearly independent. So in that sense, I mean maximal. If this is a maximal set, then k is a dimension. K is equal to the dimension. It's like, if you, I think, visualize it. See, if I choose some basis for the room, in this room, right? If you choose some basis, say this x-axis, y-axis, and z-axis, right? Then any point, I can write it as x, y, z. No, I have to give 3 informations to specify a point, right? This is the same as x times the first vector, y times the second vector, plus z times the third vector. So that tells you what is the x, y point. So the number of points is infinite, but the dimension is finite. Right? Yeah. So in the same way, Karthas algebra has infinite number of elements, but they can be expressed as linear combination of some finite numbers. Okay, so I'll see you then next week.